I'm going to give you, like they show you in the slide, in the X and Y axis, a projectile, a particle, or a mass, you know, I'm on campus, and I'm really hoping there's a thunderstorm again, right? They had power issues last time. I think that was yesterday.
Well, the thunder right now is sounding horrible.
Yeah, so I'm just letting you guys know. If you have problems with power, let me know, okay? Because
okay.
we had problems here. So far, there's nothing going on.
Well, right now you keep glitching a little.
Is it glitching right now?
A little. It's not bad. Like it will flash on and off, like your screen, your video.
Okay. But you can hear me clearly, right?
I can hear you, yes.
That's your projectile motion there. And it's gonna land X, Y. All right. What's the first step? You are going to break into two components your velocity. You're gonna label this as Bx, and I'm gonna say just label it Bx. Why? I'm gonna tell you in a second. Here you will say Vy initial. And from vectors, you should remember Px is equal to the value of V times cosine theta. And Vy initial is V sine theta. That is from chapter 3, breaking vectors into components. Now, why Vx is just Vx, not Vxi? Because we are going to assume that the object only experiments acceleration due to gravity. As it goes up and then down. So on the x-axis, we're neglecting air resistance. So we put here V on x is constant. So my first equation I can write the equation for this, which we call it the range. And you probably know that from projectile rocket launching. That's called the range. We label it R. Vx times delta t, where delta t is the total time. In fact, let's put here total. What else can you notice? This is also known as the parabolic motion. A parabola has an axis of symmetry. That is exactly the maximum point there. So we can draw that just to show you. You don't need to do that. But pretty much at the maximum point, the vertical component of the velocity is 0. But this is always constant. All across the delete lines. So we can find the maximum height. How do you find the maximum height? By using falling objects that we did at the end of last class. Now let's remember the physics behind it, right? The mass is going up, and because the vector gravity is going down, it's losing losing momentum, right? It's deaccelerating. And the other thing is that we know that here, Vy is equal to 0. Vy. So in the motion going up, and this is a motion going down. In the motion going up, the final velocity vertical is 0. The initial is Vy sine. Oh, sorry, V sine. So I don't care about time for now. We're gonna use it in a minute. But let's try to find the value of the height. So what equation should I use? If you remember, there was just one equation that you use when you don't have time. And in terms of y will be like this. By final square is equal to b initial y square plus or minus 2g delta y, which is h. Now for the maximum height, this is 0. So 0 equals to by initial, which is b sine square is losing minus 2gh max. So if I use the algebra, h max is equal to v sine theta square sine square over 2g. That's the maximum height it reaches. But I also want to know the range as a function of my given variables, not time. Now, for a projectile motion where you are launching the mass from the ground, because of the symmetry of parabolas, the time total is equal to the time to go up is equal to time going up plus time going down. Well, that makes sense. Up plus down over time. But because of symmetry, we know that the time to go up is equals to the time to go down. That's a very important result. So if I compute the amount of time to go up, I multiply by 2 and I get the total time. That's called the flying time. So let's use the other equation now. What equation can I use to find time? The simple equation B final on y equals to B initial on y plus or minus g time. To go up, we use minus. At the maximum height, because I want the total time it takes to go up, this is 0. I know this. I can find time. Yep. 0 equals to B sine theta minus G time to go up. So if you use the algebra, the time to go up is V sine over gravity. Another result, that's the time to go up. What about the total flying time? Let's put it here now. So T total will be twice the time to go up. If I use that equation, I get 2V sine theta over gravity. There you are. How about that? I know already the total time and the maximum height. But wait a second. Now I have the total time. So if I put it here, I can find what? The range. That's pretty much how we are combining what we did in falling objects and in a horizontal motion. Let's erase this. I mean, not the result already. So we found the height. And now, using this equation, if I want to find the range, what's the x zone? B cosine. What's the total time? 2V sine theta over gravity. V times V V squared over gravity. And if you remember from trig, 2 sine cosine is the sine of 2. All of this is in the slides of the book. Now, many of you probably have heard that for javelin, if you watch the Olympics, or when you throw anything at some given angle, the angle that maximizes this guy, the range, is an angle of 45 degrees. And that doesn't come from any random, just because it's half of 90. It happens to be half of 90, yes. But that's because you want to maximize this function. If you keep v squared and obviously gravity constant. So if you use the first derivative rule to maximize functions, you will get cosine, right? The cosine of what value is 0, 90. 90 divided by 2. So, I mean, or you can just think in terms of algebra, what value of sine will maximize this? 1. The sine of what angle is 1? 90 degrees. So 2 theta has to be 90. Theta will be 45 for the maximum range. Right? So that's the whole proof that you have in your book. Now I'm gonna start doing some problems using this, but hey, I'm probably not gonna be using most of those formulas. I'm gonna show you how to do the problems using the physics behind vertical and horizontal motion. I think that will keep it more simple. However, you can always have this in the question sheet. I'm pretty sure they are in there. Okay. And they will be important. I always, just to, if you're taking physics 201 during the fall, there are situations where you have to use some of these equations, electrons, protons moving in like fields. But anyway, let's go into particular example I want to show you with numbers. And then we'll do one using projectile motion, all right? Oh yeah, can I erase this now? Also, I'm recording the lecture, so if you miss anything due to like quality or anything, you can always go back. But again, right, most of this it's been covered before or is also in the textbook. But this one in particular, I didn't really see it. So let's check it out. So you're in the top of a building. And what happens is that you are going to shoot a mass or a ball with some horizontal speed. I want to keep magnitudes of this. This will be, let's make it 20 meters per second. And due to that, it's going to land. Because the object was at rest, and then you kick it horizontally, we call this free fall projectile motion or free fall project. Free fall because the initial, so Vy initial, that's 0. But you are giving it 20 meters per second. The other piece of information you need, if you want to find this value, by the way, you need the value of h. just give it to 100 meters. How will you find x? You see, you cannot use technically any of these equations because it's not really an angle there, right? The vector is just going like that. But it's simple. We can break it into two directions. Always horizontally, no acceleration. So in the horizontal, the value of x is equal to 20 times time. Where time is the time it takes to reach the ground. So it's a total time. Now, what about vertical? Well, don't forget, as soon as the ball leaves the edge of the building, gravity starts pushing it down. So the mass is gaining. Now, we know that delta y, which is the value of the height, is equal to v initial of y times time, the same time, plus or minus 1/2 gravity. The value of h I have is 100. Dy initial 0 and it's gaining. So it's just 1/2 gravity square. And if I use the, what is that question? If I use the calculator, I get 4.5. So I get 4.5 seconds. That's how long it takes to reach the ground. So then that means I can find the value of the reach. So I have the total time in the air. So here, x is equal to 20 times 4.5. That will be 45 times 2, 90. So this is 90 meters. So that's a more simplified, that's a simplified version of projectile motion. Okay. Now, there are a few things that you can be asked, and I have asked in the past on this problem. Something that students tend to make mistakes is when I ask them to find the velocity at, or the speed, not just the velocity, but the speed at any instance. And I'm gonna even go farther. What is the speed when it reaches this point? And the hint is that it's not 0. So I don't know why students tend to think that's the speed, you know? Maybe because it lands there. No, it's not. As it reaches there, it's not 0. And the reason it's not 0 is because gravity is making it go down. It's making it accelerate. So it's not possible that it's 0. And we also know that 20 there, over there, that 20 is constant. So there is no mathematically or physically possible that you get 0 for the landing speed. So how will you find, and even I can even go further, I can ask you the angle. What's the angle of the final speed with respect to the vertical or horizontal? Right? And these are things that are not covered in the equations, right? In the formulas that I show for projectile motion. These are things that are more in terms of the concepts that we have studied. That's more like vectors and motion. So to find the speed, we need motion. So to understand, we need to know what's happening. 20 keeps constant. So I can easily draw my vector is my vector's velocity here, then find the magnitude to get the speed. So my vector, my horizontal vector for the velocity here will be 20. What about the vertical? So that means that the resultant will be like this. That's my v. And the magnitude will be the speed. So how do I find this one? Let's find the vertical speed like that is by using vertical motion. So let's erase this. Yeah. And let's draw you guys a picture here explaining you what's going on. So when landing, that's 20 meters per second. And there is a, let's call this a B final now. Why? My resultant will be. So how do I find that? You know that here is 0. Gravity is pushing it down. So we can find this by using what was the time? 4.5 seconds, right? So this is 0. It's accelerating, so it's positive. And that's how we get it. 44.3. 44, which is right. So this one is 44. How do I find the magnitude and direction of that vector? The magnitude same. We get 48. That's the speed as it. To find the direction, is this one here. Oh yeah, yeah. I'm gonna keep it positive, and then you know the angle is the whole thing, right? But in this right triangle, I can just take the magnitudes, okay? Just to show, just to get the acute angle. If I do arctangent, 24.4 degrees. So you can expand on those questions and do a whole bunch of other things in there. Okay, so at least with this example and with the proof, we were able to cover basically half of this chapter, even a bit more because the rest will be circular motion. Now, let's do more problems on this. There is a more complicated situation. And I think I asked that on the exam, and it's on the web assignment. Remember the problem where, well, actually from here, the situation is very easy. What we're gonna do later is when you have this situation. So you have a rocket going up and then going down, right? We are going to do a situation like that. Yeah, we have time. But before we do that, I want to go over that example from the slide to give you. So we've done all this. That's good. We've done this. Yeah. So a simple example is the long jumper. What you guys see in the Olympics again, right? When somebody is running and then he leaves the ground at some angle and he tries to reach, right? So they give you the angle of 20 degrees, the horizontal, the speed of 11 meters per second. And then they ask you different things. How far does he jump in the horizontal? Okay. So the example from the book / the PowerPoints. By the way, guys, do you guys have the book online or do you guys have the hard copy of the book?
We have to get it from online.
Oh, so you guys have the book then?
Yeah, it's on Cengage. I believe so. Yeah.
Okay. Okay. All right, good. So they give you a jumper, it's coming running, and then it does this. So let's put here example 2. That 11 meters per second, 20 degrees. And they ask you for several things, like, first of all, they ask you how far he reached horizontally. So we know this is going to be like that. So they want you to find X. First step, we break it into components in X and Y. So By initial, B on X. So B on X equals to is there wind right now? 11 sine. Most likely going to be giving you better angles in the exam, all right? Like 37, 30 degrees, 45. But in the book, because they assume that you guys have a calculator, which I guess it's okay, but so cosine 20 times 11. Let's keep a decimal to keep it more realistic. 10.3 meters per second. Okay, 3.7. So that's the first step. Then you know this is equal to so let's find the time it takes to go up, which will be the same time as going down, and then we can find X. So, and we also need the time, so that actually is useful. To find the time to go up, at this point, Py final is 0. So Py final is equal to Py initial minus gravity time to go up. This is 0. This is this minus 9. So very easy. Is 3.8 over 9.8. What's that? As we expect, 0.4 seconds. Oh, so the total time is 0.8. So if you multiply 0.8 times 10.3, 8.2. That you find the time to go up, you find the total time, and we can also find, I believe in part C, they ask you to find the maximum height. Find the maximum height. We can use the time to go up, or here, to find the maximum height, we can use, I like to use this equation a lot, because we don't have to deal with time here. So minus 2gh. Why I like to use it? Because it's 0. This is this. So the value of h will be 3.8 squared divided by 2 divided by 9.8. It shouldn't be much. 0.7 meters. Right? It's a long jump, but it's 0.7. So 70 centimeters, right? All right. So expect something like that in the assignment. All right, there's a problem like that where you have to use part A, B, and C. So remember, you break the velocity into components, and then you can use the vertical. That's all the vertical, and that's the horizontal. So the horizontal is just that. It's good. It's always constant in there.